I will be solving problem 2.52 from Griffith's Introduction to Electrodynamics. So we have two infinitely long wires running parallel to the x-axis, and these wires carry uniform charge densities of plus lambda and negative lambda, and I've drawn that right here. For part A, we want to find the potential at any point xyz using the origin as your reference. So to start this, we will first find the potential for one infinite wire with uniform charge density lambda. So the book used Gauss's law to determine the electric field for an infinite wire, for an infinitely uniformly charged wire, and that electric field looks like this. We also have the equation for potential, which is negative integral from the reference point to field point of E dot dl, where dl is ds s hat plus s d phi hat plus dz z hat. Now let's calculate E dot dl. Now when we multiply these out, we know that s hat is perpendicular to phi hat and is also perpendicular to z hat. So taking the dot product would cancel these terms out, and these will become 0. S hat is parallel to S hat, so this will give us 1, and the dot product will be this. So now we can plug this into our equation for potential. For a bit more clarity, I will add primes on the ds and the s in the integral, just to say that s prime is a variable we're integrating over, and s is the location of the field point. So we can take lambda out of the integral because it is a uniform charge density, and with that we take out the other constants. And we are left with this. We can take the solution for potential of one infinitely long wire and apply it to our problem with two infinitely long wires. So if we do that, we would have the potential due to the positive wire as negative lambda over 2 pi epsilon naught ln of the distance from the positive wire to the field point divided by the reference point, and for the negative wire we would have lambda over 2 pi epsilon naught and the distance from the negative wire to the field point. And because potential obeys the superposition principle, we can just add these two together to get the total potential due to both infinitely long wires at a certain field point. So now what we need to do is find S minus and S plus. So here I have a drawing of the two wires as it looks on the YZ plane. And we have the distance between each of the wires, the origin, defined as A. And the S minus and S plus distance is labeled. So from this we see that S minus is the square root of y plus a squared plus c squared, and S plus is the square root of y minus a squared plus c squared. Notice that because the wire is infinite and parallel to the x-axis, there's no x dependence in S minus or S plus. So now we can substitute these into the equation we found previously for potential. And here we have our solution for part A. Part B asks us to show that the equipotential surfaces are circular cylinders and asks us to locate the axis and radius of the cylinder corresponding to a given potential V0. So equipotential surfaces are surfaces with constant potential. So we have our V equal to a given potential V0 equal to the equation we found earlier. All the terms on the right are just constants, and V0 is just a given potential. So we can set those constants equal to some constant C. Then we have the following equation. So to show that the equipotential surfaces are circular cylinders, we should put this equation in the form of the equation of a circle. The equation for a circle on the YZ plane at some y equals y0 and z equals 0, following the image of the two wires that I showed earlier, we would have y minus y0 squared plus c squared equals r squared. And when we factor this out and bring r to the left side, we get this. So we want to put this equation into a form that looks like this one. So continuing from that equation, we can multiply both sides by y minus a squared plus c squared. And we can expand these terms and do other mathematical manipulation to get it into the form that we want. So now we have something that is sort of similar to this function. So we notice that this part looks the same in both equations. So we want to define variables for these last two parts to arrive at our equation. So we want to define y naught and r. So we notice that these two are sort of in a similar form. So what we can do is try to turn this portion of the equation to look like this. So what we can do is set these two equal to each other. And we can solve for y naught. And we get this. So we took care of this and this. Another thing that's different in the equation are these. So we can do something similar. We want this portion of the equation to turn to a squared. And we can do this by defining r. So we set these two equal to each other and solve for r. And we already solved for y naught earlier, so we can substitute that in here also. And this is what we get for r. So now we can substitute in our value for the constant that we defined earlier, which was e to the power of 4 pi epsilon naught v naught over lambda. And we can find y naught and r in terms of v naught. We can multiply by e to the power of negative 2 pi epsilon naught v naught over lambda over e to the power of negative 2 pi epsilon naught v naught over lambda. So here we can use this relation where x equals 2 pi epsilon naught V naught over lambda. And this is what we get for Y naught, where Y naught is the sensor of these circular cylinders. Now we can move on to write R in terms of V naught. Again, we can multiply by e to the power of negative 2 pi epsilon naught V naught over lambda over e to the negative 2 pi epsilon naught V naught over lambda. And this time we can use this relation. Where x equals 2 pi epsilon naught V naught over lambda. And we end up with this for the radius of the cylinder corresponding to that given potential V naught. So here we showed that the equation of a circle was in the same form of our equation, showing that the equipotential surfaces are circular cylinders. And we continued to define variables Y naught in terms of V naught, where Y naught represents the axis of the cylinder corresponding to that given potential, and R, which corresponds to the radius of the cylinder corresponding to that given potential.